Hello everyone, welcome back to Chemical Engineering and Aspen channel. As you know, these days we are focusing on the module of Chemical Reaction Engineering. So in this regard, we are bringing the lecture number 23 for our valuable viewers. I'm your course instructor, Dr. Mohammad Haris Humayun, working as Assistant Professor of Chemical Engineering. So in our previous lecture, which was lecture number 22, we have developed some equations related to CSTR design, and now we will practically apply these equations in example number 5.2, which is related to CSTR design. So let's first read the statement and then accordingly we will solve it. So the statement is that close to 16 billion pounds of ethylene glycol were produced in 2013. It previously ranked as the 26th most produced chemical in the nation on a total pound basis. About one half of the ethylene glycol is used for antifreeze, while the other half is used in the manufacturing of polyesters. The polyester category, 88% was used for fibers and 12% was used for the manufacturing of bottles and films. The 2013 selling price for ethylene glycol was $0.6 per pound. So this is the overall overview of our product, which is ethylene glycol. Now, it is desired to produce 200 million pounds per year of EG, which is ethylene glycol. The reactor is to be operated isothermally. You already know that we are focusing these days on the isothermal design. So, obviously, we will solve an isothermal reactor. A 16.1 mole per cubic decimeter solution of ethylene oxide EO in water is mixed. We will see figure in the next slide with an equal volumetric solution of water containing 0.98% of catalyst, sulfuric acid, and fed to a CSTR. The specific reaction rate constant is 0.311 per minute as determined in example 5-1. We have already solved that example for batch reactor where we had determined the value of the reaction rate constant that came out to be 0.311. Practical guidelines for reactors set here are given by Mukesh. So this is the overall overview. We have been given the capacity which is to be produced is 200 million pounds per year. We have been given that the system is isothermal in nature. Isothermal reactor temperature will remain the constant. We have been given the value of specific reaction rate constant, and we have been given the value of the concentration, which is 16.1 mole per cubic decimeter. Now, there are three tasks which we have to do. Number one is if 80% conversion is to be achieved, determine the necessary CSTR volume. So, X is given as 0.8. We have to determine the value of V. Second, if two 800 gallons reactors were arranged in parallel with the feed equally divided, what would be the corresponding conversion? First case, 1 CSTR, X was given, we had to determine V. Second case, reactors are in parallel, the volume is given, we have to determine X. And in the third case, again, we are given the volume of the reactor, but now these are in series. If two 800 gallon reactors were arranged in series, what would be the corresponding conversion? So in that case, 80% is given. In these two cases, we have to determine what would be the conversion for the system. Now, first we calculate FA naught and F of C. Why is it so? You will see it in a couple of minutes. So we are assuming that ethylene glycol is the only reaction product that is formed in the process by EO, which is ethylene oxide and water reaction in the presence of the catalyst, which is sulfuric acid. So A plus B goes to C. Accordingly, if you see this diagram, which was referred in the statement, that this is the CSTR obviously, FA naught, VA naught, CA naught 1, FB naught, VB naught, CB naught 1. These two combine, this A represents ethylene oxide and B represents water. And these are fed to this CSTR with volumetric flow rate as V naught, concentration as CA naught. Once the reaction takes place, we get F of C. So first we convert our product, which is F of C, into mole per second. So accordingly, we have been given it is 2 million pound per year. So 2 into 10 raised to power 8 pound mole per year. 1 year contains 365 days. You cancel out. 1 day contains 24 hours. Day is cancelled out with day. 1 hour contains 2600 seconds. So this hour is cancelled out with this hour. And we know the conversion from pound mole to gram. Accordingly, 454 grams is equal to 1 pound mole. So pound mole is cancelled out with this pound mole. And accordingly, for ethylene glycol, 1 mole contains 62 grams. Accordingly, that will convert to mole per second, and that is 46.44 mole per second, because we are just simplifying the system in terms of molar flow rate. And if you look at the stoichiometry, or if you go back to your stoichiometry concepts, f of c is equal to fa naught x. And accordingly, for 80% conversion, fa naught is equal to fc over x. 46.4 divided by 0.8. So accordingly, fa naught, which is the initial flow rate, is 58.05 mole per second. That information was not given to us. So you can see now that why we have taken the first step, because we need to know what is the flow rate of the limiting reactant, which is ethylene oxide EO in our system. We will first apply the algorithm on the single CSTR. The algorithm is mole balance and design equation. So V is equal to Fa naught x over minus Ra. For rate law, minus Ra is equal to Kc. It has been given in the statement that water is in excess. So once a quantity is in excess, if you remember the example 5.1, that actually was given over there as well, and that is the carry forwards of this one, because if you remember example 5.1, and I will give its link in the pop-up link as well, that water was is in excess. So accordingly, we had said that Cb will not play any part in the rate law equation. So that is why it is not included here as well. For stoichiometry, for liquid phase system, V is equal to V naught. Accordingly, Ca is equal to Fa over V. C is the concentration, F is the molar flow rate, V is the volumetric flow rate. Fa is equal to Fa naught into 1 minus x, V is equal to V naught. Fa naught over V naught goes to C naught into 1 minus x. Once we combine these, that will become, this equation will become V is equal to Fa naught is replaced by V naught Ca naught into x, and minus Ra is replaced by Kca, and C is replaced by Ca naught into 1 minus x. So that Ca naught is cancelled out with this Ca naught, that will become V naught x over K into 1 minus x. And for evaluation, now what we need to do, we need to first find the parameters. We know Va naught, and that is equal to Fa naught over Ca naught. Fa naught is 58.05 as we have seen. Ca naught is 16.1. So accordingly, that will come out as 3.606 cubic decimeter per second. And if you go back to the statement, that Va naught is equal to Vb naught. So we have calculated one parameter, and accordingly, second parameter is estimated. And Fb naught is equal to Vb naught into Cb naught. Now we do not know the value of that Cb naught, and that is not given in the equation, but we are given that it is in excess. So once a quantity is in excess, what we can do, we can simply apply the density method over here. How? Let me show you that first. Vb naught is 3.606 as it has been computed over here. For Cb naught, we know the density that it is 1000 gram per cubic decimeter, and 1 mole contains 18 grams. So gram is cancelled out with this gram, and accordingly it will be mole per cubic decimeter. So accordingly, we get Fb naught is equal to 200 mole per second. So you can see that it is in huge amount, and accordingly there is the change in concentration is neglected in the system. Accordingly, the total V naught is equal to Va naught plus Vb naught, and accordingly it is 3.606 plus 3.606, and that is 7.212 cubic decimeter per second. We have been given K, that is 0.311 per minute, or if you convert it to second, that will be 0.0052 per second. Accordingly, V is equal to V naught x over K into 1 minus x, the equation which we have developed. For the single CSTR, V naught is 7.212, x is 0.8, K is 0.0052, 1 minus x, obviously 1 minus 0.8 is 0.2. Accordingly, we get V is equal to 5548 cubic decimeter, or 5.548 cubic meter, or 196 cubic feet, or 1466 gallons. So that is the first one for our system for the single CSTR. We need a reactor volume of 1466 gallons, or 5.548 cubic meter, to get the required conversion. Now we will move to parallel reactor and we will move to the series reactor. In that case, we have been given that there are two 800 gallons reactors present and we have to find the conversion of